Saya kira dimulai nih, karena
Ya,
kita.
Prof, kami mulai, Prof.
Oke.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon
Waalaikumsalam.
and welcome, ladies and gentlemen. My name is Rosani Taniswiasari. It's wonderful and precious change for me to be your master of ceremony in this beautiful day on 30th of April 2025. The Honorable President of the Indonesian Mathematical Society, IndoMS, Professor Dr. Andes Davik, MSc, PhD. The Honorable Speakers of this international seminar, Professor Marco Fahkonen and Professor Dr. Andes Basuki Widodo, MSc, PhD. And distinguished guests, ladies and gentlemen. Welcome to the International Seminar Advances in Computational and Applied Mathematics. First of all, let's say thanks to Allah who has given us guidance, happiness, healthy, and mercy so we can attend and participate in this event without any obstacles. Praise and salutation upon our Prophet Muhammad Sallallahu Alaihi Wasallam. Ladies and gentlemen, we would inform about our today agendas. Please allow me to read several sequences of our agenda. First, opening session. Second, singing national anthem of Indonesia. Third, opening remarks from President of IndoMS. Fourth, presentation from speakers. And last, closing. Ladies and gentlemen, to take advantage of the time, let's start agenda by reciting Basmalah together. Bismillahirrahmanirrahim. Step to the following agenda, singing national anthem of Indonesia, Indonesia Raya. To those on duty, please welcome. Thank you. Next on the agenda is the opening remarks from the President of IndoMS, Professor Dr. Andes Davik, MSc, PhD. Please welcome Professor Davik.
Thank you, Anis. uh, Honorable Professor Marco van Honen from Industrial Physics and Mathematics Department of Technical Physics, Faculty of Science, Forestry and Technology, University of Eastern Finlandia. And Honorable Professor Basuki Widodo from Institute of Technology, Surabaya, and also the head of Mathematics Department of the University of Jember, all the faculty members, and all the lovely participants. Today we have IndoMS Seminar on advanced and what computational and applied mathematics. Maybe I should describe first about IndoMS. IndoMS stand for Indonesian Mathematics Society. We have this organization since a long time ago. And we have a lot of mathematics faculty members, either from mathematics education and pure mathematics, join of for this society as a member, and we regularly develop a program on three focus normally in the staff development and teaching, also curriculum and teaching and model, innovation technology, as well as we are also focusing on the research activities and maintaining some journals, either they are indexed by Indonesian journal indexing site, namely Sinta, as well as also indexed by Scopus or WOS. And mainly, we also doing research on applied mathematics and combinatorics, also in analysis, statistic, and even also in ethnomathematics, historical mathematics, machine learning, and other research of interest of mathematics study. So we are happy to have Marco Vahonen as a permanent guest, international guest of the University of Jember. Even your visit in the
Catatannya hanya
short
30.
time period, I'm very delighted to say thank you very much for your visit, because your visit is not only visiting us as a guest, but we will follow up by tightening the collaboration in mathematical research of interest, especially in applied mathematics. So please, Anis, also see whether Professor Basuki already joined with us or not. Yeah. If yes, please
Yes, sir. He's already with
This
us.
already, okay. So again, Professor Basuki, he is an active researcher, and there are a lot of students already supervised by him in the master degree and PhD degree. He is a very productive researcher in applied mathematics. So I'm very uh, helpful, and also by the what productive collaboration by him, because there are a lot of what staff from University of Jimber already graduated from his university. So by those two invited speaker, I believe this seminar will be benefiting to all of you. So I'm congratulate and also declare this IndoMS seminar open, formally open for all of you. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you for your opening remarks, Professor David. Ladies and gentlemen, we are now entering our main agenda, the presentation by our speakers. Professor Marko Fokkonen from the University of Eastern Finland and Professor Dr. Andes Basuki Widodo, MSc PhD from Institute Teknologi 10 November. The session will be moderated by M. Ziaul Arif, MSc PhD from the University of Jember. Please welcome Ziaul Arif, MSc PhD.
Thank you, Anis, Master of Ceremony. Thank you so much for this time. Good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, welcome again to all participants joining us today from across Indonesia or perhaps some other universities in Indonesia. I'm Dr. Zaul Arif from University of Jember, and it is my pleasure to guide you through today's exciting seminar session, IndoMS Seminar on Advances in Computational and Applied Mathematics. Yeah, so we are proud to present two outstanding speakers who will share valuable insights on developments on computational and applied mathematics. We hope this session will give us some ideas, collaboration perhaps, and provide inspiration for all of us. So, dear participant, we divided the session into two parts. The first part is the presentation session. Each speaker will be given about 60 minutes to present their works or their research. And second is the question and answer and discussion session, about 30 minutes, where you may address your questions to both speakers. Okay, before we begin the presentation, allow me to briefly introduce our two distinguished speakers. Our first speaker is Professor Basuki Widodo, MSc PhD. Professor Basuki is a professor on mathematical modeling and computer science simulations at ITS Surabaya, Institute Teknologi 10 November Surabaya. He completed his master's degrees and his PhD from Leeds University, UK. He has an extensive background in dynamical system, mathematical modeling, computational fluid dynamics, applied mathematics, and other areas of engineering mathematics. Throughout his career, he has held various leadership positions, including chair of the Department of Mathematics, dean of the Faculty of Mathematics and Natural Sciences, and later dean of the Faculty of Mathematics, Computing, and Data Science at ETS. He also served as chief and advisory chief of the IndoMS for East Java. Professor Basuki is widely recognized for his dedication and to advancing applied mathematics in Indonesia and also actively mentoring young researchers in Indonesia. His publications are widely recognized in national and international forums. Professor Basuki, thank you so much for joining us today. We are truly honored to have you here today. Good afternoon, Professor Basuki.
Good afternoon.
And our second speaker is Professor Marco Vauhkonen. Professor Marco is a professor of industrial physics and mathematics at the Department of Technical Physics, University of Eastern Finland, Kuopio, Finlandia. He earned his PhD in physics from the University of Kuopio. Now, name is University of Eastern Finland. His professional journey includes various academic and research roles. But beyond the academia, Professor Marco has contributed to industry as a chief technology officer at Namcor Ltd, now is Autotech under Metso Company, and also chief science officers at Roxol Ltd. It is the company of the measurements technology. He leads the computational physics and inverse problem research group and has strong international reputation in inverse problem tomography, computational physics, and other cutting-edge application of mathematics in physics, also in engineering. So he has collaborated extensively with academia and industrial partners, including research project funded by the Academy of Finland and also European Union. He works proof how mathematics can solve the real problems through powerful modeling and application of mathematics. So please welcome Professor Marco. We are truly honored to have you here today. Good afternoon, Professor Marco Vauhkonen.
Good afternoon. Thank you.
Dear participant, without further ado, let us now begin with our first speaker, Professor Basuki Widodo. Professor Basuki Widodo, you have about 16 minutes for your presentation. And now the screen is yours and time also is yours. Please, Professor Basuki Widodo.
Thank you very much, Mr. Zaul Arif of the MC. Yeah, it is a great pleasure to me, yeah, to present a part of my research in this seminar. So, my name is Basuki, yeah, from ITS, and now I will let me share our PowerPoint. Okay. Can all of you see the
Yes.
my
Yes,
presentations?
Professor.
Okay, thank you
Yes.
very much. Thank you very much. Okay, now I want to talk about the magnetohydrodynamics nanofluids flow through a vertical porous cylinder. This is quite interesting, yeah, for knowing or for understanding of the magnetohydrodynamics characteristics of the nanofluids. Because this is very interesting, so I want to explain to you, or I want to share the research here concerning with that one is sometimes you can see in power generator, the power generator actually using in Indonesia using what is that fuel sorry diesel, yeah, diesel. But in outside of this country, I mean on abroad, sometimes using nuclear power generations. So this is I want to share what is when the fuel of the power nuclear power generation is operating a very long time. This is our research. Yes. Okay. I want to let's say I want to first talk about the magnetohydrodynamic. What is the magnetohydrodynamic first? The magnetohydrodynamic is a study about fluid movement that affected by magnetic field and cannot conduct electric current. So the basic of the concept of magnetohydrodynamic is magnetic fields can induce current electricity in a conductive fluid that moves. So it produce the force in the fluid and also alters magnetic field itself. Yeah. So that's why the explorations of magnetic hydrodynamic application is a very important thing, because this is very important to know about the what happened in operations of, for instance, in a power station using a nuclear reactor, or maybe in a generator of magnetohydrodynamic reactor. So this is the key point of our research to know what happened when the power generator is operating in a long time. Yeah. Okay. I want to show you. Let's say here. Yeah. So this is the nuclear power generations, and this is the nuclear power plant diagram. So the electricity can produce from the turbine when then moving to the generator, so produce the electricity. But what happened in a turbine? In a turbine, the stream of the what is this of the water flowing from the stream generator to turbine. Yeah. And then what the product of the steam generator is steam. Yeah. And steam can be produced by reactor. So this is a nuclear reactor. Nuclear reactor can produce the heat. So how to produce the heat? So this is the problem. So heat here. So the heat can be produced from the calandria tube, yeah, and in the calandria tube compresses of the long cylindrical fuel, yeah, and inside of the cylindrical fuel we have look here fuel rod, yeah, and each of zero rod comprises of a lot of fuel pellet. This pellet is from uranium, yeah, uranium, enriched uranium, not pure uranium, but enriched uranium, in order to make or to produce chain reaction, and finally to produce the heat, and the heat can be used using using the here fuel rod inside and on side of the fuel rod here. So the problem my concern of the research is here, yeah, that one. This is solid cylindrical fuel rod, yeah. If the power plant what is that operating in a long time, so can be I mean the cylinder rod can be make a hole here, or it that's mean that the solid of the cylindrical fuel rod can be porous. So what is the problem when the fuel rod is porous? So is it dangerous or not? So this is our interesting to study of the problem here. So let's say for another thing is a nanofluid, yeah, because when the solid becomes porous, so it can be entered by some fluid like nanofluid, because nanofluid is measures is a very small thing, so can be put it in the porous. So this is this is the problem. So what is the nanofluid? Nanofluid consists of the basic fluid actually containing a dispersion of nanoparticle. So nanoparticle can be ferro, can be lithium, or can be any material of the thing. Yeah. Okay. So what is the interesting? What is the interesting of nanofluid? The interesting of nanofluid is to increase the effectiveness of thermal conductivity, because there is a small particle measures nano. Yeah. So the nanofluid can also increase the basic of fluid viscosity, because the fluid becomes viscous. So this is the uh, what is that? The problem, or means the useful of the nanofluid. So let's say here is our research. Yeah, suppose that one is cylindrical field rods, and then to be placed in some place here, and then we have actually, when we can see here, yeah, so the fluid can flow from bottom up to the using stream flow. Yeah. So now this is the this diagram of physical problem. This is the road, and this is porous. Yeah, this is the porous. We we suppose that one is a porous, and this is the fluid comes from the bottom up to the up. Yeah, by using some pressure here. So this is the mainstream when flowing through the cylindrical rod. Yeah. So this is porous cylinder. So what happened when the stream or the fluid comes from here? So we want to know what is the temperature and what is the velocity. Why we intersect in the velocity? Because we know we want to know when the velocity becomes increased. So what happened there can be bombarded by the particle nano. So the hole becomes bigger and bigger. So this is the problem. And for the temperature also, when the hole become bigger and bigger, so the temperature here, for instance, here can be higher and higher. So this is the problem. So this thing can be melting. Yeah. So this is our problem. So we want to know what is the velocity and what is the temperature. So when we make the formulations here, so we have to see the conservative law. Yeah, we have 3 conservative law using here. For instance, is mass conservations, and then momentum conservations, and also because we want to know the temperature, so we have to use the energy equation, energy conservations. So when we try to make a model, so we have this model from the mass conservations, and this is from the momentum conservation, and this is for isolation, because we interested in two-dimensional. So we suppose we use x and y in our coordinates here. So now we from here we have these equations. So we have these equations. So this is we call dimensional equations. Yeah. So now, if we want to know, if we want to write, or if we want to produce mathematical model, so we have to change into non-dimensional variable. Yeah. So we introduce this variable for x. This is a is radius of the cylinder in the base of cylinder, and y is proportional to Reynolds number, and p is pressure, yeah, pressure here, and t is proportional to temperature in a wall and temperature outside the wall. So TW is the temperature in the wall, and T infinity is temperature outside the wall. I mean, not related to the distance, but that one is it's just a symbol. The infinity, that's mean that the temperature outside the wall, yeah, in front of the wall. And this is a U velocity, yeah, and this is U is a velocity in towards x-axis, and V is a velocity in y-axis. So this is non-dimensional variable, and then when I substitute in previous our dimensional model, so we have non-dimensional model look like here. Yeah, so this is for continued equations. When I introduce in momentum equations, in mass conservations, and this is from momentum equations, and that one is for from energy equations. So we have 1, 2, 3, 4. Now we want to solve together, yeah, using some methods. We call it here. So we for the first, yeah. So we introduce the boundary layer theory. So concerning with the density. So when rho density of rho. So when density, when we embed to the or insert into continuous equations, so this is satisfied. So that's why this is we can because satisfied, so we can remove from the previous equations. So when we have when we use boundary layer theory, so we have momentum equations becomes like here. So this is the notations of the intensity, magnetic intensity, and this is for volumetric, and also another symbol. And for the momentum equation in y-axis, so we have that one. So the pressure actually, or gradient of pressure actually is a 0. That means that pressure in x directions is constant. So we need to know the pressure, yeah, of the variation of pressure in a term of the y-axis. So this is the system. So this is can be removed as well, yeah, because P is a constant in a x direction. So we have 2. So from the fractions we have 4 equations, and now we have 2 equations. So momentum in x directions, yeah, and also in energy equations, yeah. So meanwhile, for nanofluid equations, so we have the formula of the density and viscosity and the specific heat and thermal conductivity. This is this formula respectively, yeah. So this is I want to put together, yeah, into the momentum equations and energy equations. So we have these equations. So we have these equations, yeah, And now we have actually two. So we have four equations when without none of it, and that one is for using nanofluid. Okay. Now, because you can see here, it's very complicated. So I want to introduce this is the stream functions and velocity potential. So we need to know what is the stream functions. Yeah, what is the stream of the fluid flow. So this is the problem, our key point of the research. So now I want to introduce the stream function. The stream function is the function of equal to x and function of x and positions of the particle or particle of fluid or particle and nanofluid. And T is the temperature in these positions. And U and V, yeah, define as that one is U is the gradient of stream functions respect to y-axis, and V is gradient of stream functions respect to x. So when we put it in the precious equation, so that one is satisfy the equations of mass conservation. Now when we formulate again, so now we have the velocity of E is 3/2 sine x. Yeah, so that's why when we derive into x into x, so we have that one. And also this is the definitions when we have derivative of f respect to eta. So we denote by f dash, and the derivative, the first derivative of theta, temperature, respect to the positions of its position of the particle on fluid. So we denote by theta dash. That's why when we continuing the process, so we obtain the momentum equation, then energy equation looks like here. So it's very simple. So you can use Rangakato to solve, and then energy equations here using Rangakato of the port. Or you can use another method. So now from here, so I use Keller box method. So what is Keller box method? Keller box method is the series of the method applies here. So this is the process of the Keller box method. So first of all, we have to reduce in order becomes first order equations. After this, so we make or we have to discretize using finite difference method. From this side, from this year, so we use central difference because for central difference the accuracy is very good. As far as I know, when we use central difference is satisfies of the accuracy. So after this, so we need to linearize using Newton method and then solve the equations. So from this one, so we can make algorithm of the program. So from here, I use MATLAB to produce the results. Yeah, the results. So first of all, for the nanofluids, we use the particle. The particle is lithium oxide. So when we lithium oxide put it into the water, so we have the nanofluid. So when we put it into the equation, so we have the solution looks like here. So you can see here. So we make variations of the magnetic parameters. So this is become higher. Yeah. So you can see here when the magnetic the intensity of magnetic, or when parameter magnetic is higher or increase, so the velocity become decrease. Become decrease. So this is the problem. Means when uh, we now we have the knowing, yeah, we have the knowing that when we increase the magnetic parameters, so velocity become increase, and also the temperature become decrease. So the temperature become decrease as well. So this is a very good thing when because if the magnetic parameter we use increases, yeah. So we hope that the the velocity become decrease, because in a problem, if the velocity become decrease, so the fluid can bombard the cylindrical solid. So that one makes the hole becomes wider. Yeah. So when become wider, so this is become the performance of the cylinder of the road fuel can decrease. So this is our knowing. Yeah. So also when magnetic parameters become decrease here, so the temperature become increase, so the temperature become decrease. So this is a very good thing. Yeah. Now, when we what is the parameter porosity parameter can be variations, or what happen in variation of porosity parameters. Okay, see, you can see here when the porosity parameters make increase, so the velocity becomes decrease, and also the temperature when porosity parameters increases, so the temperature become decrease. So this is very good. Yeah. So I have some knowing now for the characteristic inside of the problem. Okay. Now, what happened when volume fraction parameter? Volume fraction is a ratio between phase fluid and the particle of the nano. That means that when the higher of the volume fraction parameter, so the nano particle uh, is more number, yeah, or number of nano particle. So this is you can see here when the volumetric parameter is increased, so we have the velocity becomes higher, and also the temperature become higher. So that's mean that this is not very good, yeah, because if the nanofluid, yeah, put it into the fluid, this fluid becomes more, yeah. So that one makes the velocity become higher, and for the temperature become higher as well. So that's mean that this is very dangerous. Yeah, yeah, very dangerous. When we put nanofluid increase. So this is the ratio of the Prandtl number and parameter. So this is Prandtl number is parameter is the ratio, yeah, between conductivity and thermal conductivity and conductivity. So you can see here when we increase the Prandtl number, so the velocity here becomes higher, but the temperature become lower. So this is we have the knowing, yeah. So when we increase the Prandtl number, that means that the nanoparticles come higher. So that's why the speed of the velocity becomes higher. So this is the problem because can be make bombardment of the solid cylindrical. So this is very dangerous. So that's why we do need recommend of this increasing of the Prandtl number. So what happened when we use particle of ferroxide? So this is you can see is looks like the effect of the lithium oxide. You can see here when we increase the magnetic parameters, and also when we increase the porosity parameter. So the effect of the nanofluids uh, of the fluid can make that one. This is okay. This is the same with with the lithium oxides, and also for the volume fractions. Volume fraction is the same, and Prandtl number also the same. So this is our solutions here. Okay, for the conclusions. So you can see here. So from lithium and ferroxide is very good thing to make or I mean good of the nanofluid here, lithium oxide and ferroxide fluid can be used can be used for knowing the characteristic of the cylindrical fuel rod nuclear power using our mathematical model. So the characteristic of that one is pretty good, yeah, of the results. So this is our conclusion here, yeah. Velocity nanofluid increase when the parameter of magnetic and porosity increase, while the volume fraction and Prandtl number increase, so the temperature and nanofluid increase when the parameter magnetic rose and Prandtl number decrease while volume fraction is increases. So this is the results from our view, yeah, or from our mathematical model. So that's it. Thank you very much. This is for references. Thank you very much. I back to the MC. Thank you very much.
Thank you. Thank you. Thank you so much.
Farid.
Yes, thank you. Thank you so much, Professor Basuki Widodo, for the inspiring talk. Yeah, that's an interesting topic. The topic is quite common, I guess, in processing industries, for example, like nuclear and other processing industries, I guess. As we can see here, mathematics can be applied to solve the problem in industries. So, to all participants, please hold your questions for...
Pak Z, I
Yes,
believe
yes.
you can ask participant to ask a question because Prof. Basuki will depart soon, I believe.
Oh, yeah. Okay.
Yeah. If
Okay.
there is
Yes,
there is
Prof.
time from
David.
participant to ask.
Thank you for reminding us. Okay, to all participants, if you have any questions, please just write your question in the chat, or maybe you can raise your hand and directly ask to Professor Basuki Widodo. Kindly mention your name and affiliation when speaking or when you write in the chat, please. Okay. Any questions for the participant from the participants?
Pakai bahasa Indonesia tidak apa-apa, partisipan.
Ya, silahkan Bapak Ibu. Mungkin kalau ada yang bertanya dalam bahasa Indonesia, kami akan coba untuk mentranslate. atau ya silakan dituliskan di chat boleh atau raise hand dan langsung ke pertanyaan ke Prof. Basuki Widodo. If not, may I have question, Prof. Basuki Widodo?
Yes, please.
Okay, have you been collaborating with some kind of industries in Indonesia? Because I don't think we have kind of a chamber or nuclear industries in Indonesia as you shown in the slide. Thank you.
Okay, yeah. Thank you very much. Actually, that one is our research, collaborations with my partner in Malaysia, Pahang, and UTM Johor, and also my partner in UK.
Oh, that's
With
so great.
yeah, UK. Yeah, so the data what I have is supplied by my colleagues from UK, from Leeds University.
Oh yeah, yeah.
Yes,
I see.
and that one is our is what is that? Produce some results, and uh, a lot of PhD students also produce in Pahang, and also in UTM as well. Yeah, and
Okay.
from when I try to introduce to our colleagues in Indonesia, so that one is the problem. Yeah, because we don't have big power plant and nuclear power plant in Indonesia.
Yeah, yeah.
We have small, yeah, in close to ITP. We call Batan, yeah, Batan.
Oh
But
yes,
now
Batan. Yeah,
we know for Brin, yeah, Brin.
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 Yes.
Yeah, in the previous, the name is Batan, but this is very small to implement of the uh, power generations, electrical power generations.
Okay.
So that one is what I have to know. I have to show you, or I want to explain to you. Thank you very much, Pak
Thank
Jaul Arif. Anyway,
thank you, Prof. Basuki Widodo. Thank you so much. Yeah, be challenging if we apply in
yeah,
Indonesia because we
yeah,
don't have any data. But yeah, it could be possible for the
yeah,
future, I guess.
yeah. So,
Yes. Okay.
thank you very much.
Any
So
question
first
from
of all,
participants?
I want yeah. First, I want to uh,
Yeah. And
apologize
okay. Yeah.
in any inconvenience, because my flights
Quite soon. Yeah.
is yes, yeah, that's soon.
Okay.
So thank you very much, Prof. David,
Yeah, matur
uh,
nuwun, Prof. Bas.
for your
Masih.
invitations. Yeah,
Thank you
yeah,
very
and
much.
also yeah, for the Prof. Marco on off. Sorry, sorry, to apologize. Cannot um, cannot see or cannot see your presentations because our flights is soon possible. So thank you very much. So I
Thank you.
want to leave possible. So
Thank you. Yes.
Yeah,
sorry about that. Thank you very much.
thank
Thank
you.
you very much, Professor
Yeah,
Widodo, for your
matur nuwun,
time.
Prof.
Thank you.
Bas.
Yeah.
Have a
Yeah.
nice and have a safe flight.
Flight. Have a
Thank,
safe flight.
thank you, Prof. David. Sorry about
Yeah,
that. Thank you.
No worries, Professor Widodo. Thank you
Yeah,
so much for your time.
thank you.
Enjoy your flight.
Thank you very much.
Yes, dear participant, now we are moving to the second speaker, Professor Marco Falconen. You have also have about 60 minutes for your presentation. And now the time and screen is yours. Please share your screen and then you can start. Okay, yes, we can see your slides.
Okay, I just put it on presentation mode if I like
Yes.
that.
Okay, yeah.
Okay, thank you first for inviting me to give this talk. It's a great pleasure, first of all, to be in Chamber and give this talk in this IndoMS seminar. So today I'm gonna talk about a bit of inverse problems and some applications mainly from our university, University of Eastern Finland. I will show some results also from my collaborators in Austria, for example, and also my collaborators in UEF. So I've traveled a bit about a week ago. So we are here on the right-hand corner, and here is Finland, where I came from, and our university is in Kuopio, and actually it's a unification of two universities, one from Joensuu, University of Joensuu, and University of Kuopio. Now it's University of Eastern Finland. And distance between these campuses is 150 kilometers, so not a walking distance between campuses.
Yeah.
Some pictures from the city of Kuopio in summertime. It's in the Lake District, so you can see a lot of lakes. Also here, in wintertime, you can go ski jumping if you are brave enough or have a steamship cruise on a lake, or just hang around in the city center. There's a city hall of Kuopio in this picture on the lower left side. And everything changed for winter. Now we are in the springtime, so we just got all the ice melted from the Lake Kallavesi. But in the middle of winter, you can go skating there, or you can go skiing in the forest, or have a look at the northern lights, or have a nice and refreshing swim in the lake after making a big enough hole there. Okay, then to the actual contents of the talk. So I introduce our group and tell you a bit of theory on inverse problems and give some two simple examples, and then tell Bayesian inversion, some of our research directions before going to some applications. So I mainly talk about electrical imaging, which is a method to make tomographic imaging using electricity or electromagnetic field or capacitive field. And I show some examples in industry and medicine, and then few words on electromagnetic flow tomography. This is a project that we worked together with Dr. Ziaul Arif while he was working for me as a PhD student in our university a few years back, and some practical examples from that one as well. So here's our group, about 40 people. So I'm not the only professor. We have full professors of 4, and then one kind of half professor who's also head of the department. One research director, about 13 postdocs. Some of them are also lecturers, so no time to work full time. And then a bit more than 20 PhD students currently, and a couple of technical personnel. We have physics department, so we also build some devices by ourselves. Here's our group few years back, so it has grown quite a bit from this, and there's Arif in real work in our laboratory. In Finland, this inverse problems community is very large, and we have done collaboration with other universities in Finland since basically 2008. We have got funding from the Academy of Finland or Research Council of Finland nowadays, and almost all, not quite, universities and Meteorological Institute are part of this inverse problems community. And we at the UEF, we started these studies in 1990s around, when I did my PhD and master's work on inverse problems. We also have funding from this kind of flagship. This is kind of continuation of this inverse problems research. So here we try to kind of have more impact, so more applications of the inverse problems with industrial partners and other stakeholders. So for those who don't know about inverse problems, so I try to explain a bit of those. So aim is basically to calculate estimates or estimate parameters that you cannot directly measure or observe. So what you do is you make some measurement that is not the parameter that you are interested in. Then you have some mathematical model, normally coming from physics, normally being a partial differential equation or differential equation, or something similar physical model. And forward problem is so that when you know this theta, which is your primary interest parameter, you can calculate through this model your outcome, your measurement. So this cause and effect kind of line. And of course, inverse is just vice versa. So you measure this y here, and you try somehow to invert this model to obtain estimate for this unknown parameter theta. And this x here is some fixed and known parameter that you are not interested in, and this e here is noise. And very simple kind of one parameter problem is mercury in glass, which is used to measure temperature. So you don't actually measure temperature directly, but you measure the height of this mercury column in this mercury in glass thermometer. So warmer it is, the higher is this mercury column in here. And this mathematical model is easily obtained from thermal expansion law in physics, or you can even use calibration, easy calibration to get the line. It's linear between those two parameters. And when you know this model, when you measure the height of this column, you can directly say what is the temperature. And this is an old simple inverse problem. And another a bit more complicated is tomographic imaging using X-rays, so this kind of X-ray CT. So this kind of more simple is what is normally used in hospitals when you have some problems, for example, swallowed a fork, and you're taken to the hospital and they take X-ray image. This is fine, but if you want to have this kind of tomographic image, so this kind of a layer of your body at certain level to see what's there in the inside of your body, then you need to make lots of these projections from different directions of the patient. So you have sources, for example, here on the left-hand side of the body. So this is now 3x3 pixelization of your innards on this line here, and you apply X-rays from very different points, and depending on the attenuation, these measurement values differ. You have a detector on the other side. But this is not enough data. You have 3 measurements here and you have 9 unknowns here. So this is the forward problem when you apply these X-rays and calculate the outcome. So you need several projections. So you can project or send X-rays here and measure on the opposite side, or send X-rays here and measure on the opposite side. So for example, these 3 projections produce 11 measurements, and you can write down simple linear system of equations out of it, and you can solve basically these values that are of interest. So as said, forward problem is to compute the projection images when the X-ray source and the internal attenuation coefficients are known. So when you know these, you can calculate these in the simple example by adding these numbers, and then also take into account how long is the distance at each pixel. So this is assumed to be 1, this edge here. So for example, this ray travels square root of 2 because it goes 45 degrees through this pixel there. So the outcome is 5 times square root of 2. And in the same way, if it goes to some other locations, you just need to calculate the length, how much the ray spends on the pixel. So you write down the system of linear equations and you get the model of this. An inversion is of course inverse of that. So you measure these values, these outcomes, and the question is, what are these attenuation coefficients? So what are these? What is actually the tomographic image there? So you can write it down as A theta equals Y. So this A matrix comes from the discretization of the previous X-ray applications. Theta is the image, it's a vector. So A is a matrix of size measurements times the unknowns. Theta is a vector of n times 1, so n is number of pixels, so 9 in this simple example, and y is a vector of measurements, so length of m. So in this example, it was 11. So basically, this is overdetermined system of linear equations, and there's no no solution for this in general. So in inverse problems, one approach is to use least squares solution. So you minimize this kind of a squared norm. And the solution is through normal equations, as we easily know. So you get estimate, least squares estimates using this equation formally. You never calculate the inverse like this, but formally it comes like that. But the problem often in inverse problems is that the problem itself is ill-posed, and this, for example, A transpose A becomes severely ill-conditioned, so you cannot invert it. Or sometimes you can, but the outcome is complete rubbish. And we need to regularize. So in the ill-posed problems, we add, instead of using this least squares norm only, we add a regularizer here. So it stabilizes this otherwise ill-posed inverse problem. So here we have new matrices. L is so-called regularization matrix, and alpha is a small number bigger than 0 that kind of handles the weight between this so-called data space and this so-called Fourier regularization space. And often this L is written so that we assume that theta is smooth. Simplest is that it's identity, then it doesn't promote smoothness in the solution, but normally it's some kind of difference matrix to make this solution smooth. There are others, but that's very common. And the solution is easy to show to be like this. So what you end up having is this regularizing term. So not only A transpose A, but you add alpha L transpose L. So now this is invertible. It can be easily shown through match theory. But what we normally do is that here we don't assume anything about basically statistics of the noise, nor we assume anything about statistics of the prior, so of this L. So this is kind of deterministic approach. And if we like to do statistical inversion, we end up using Bayesian inversion approach. So in here, the aim is actually, or first of all, we assume that all unknown variables are considered random and they have probability densities. This may sound a bit weird, but it's very efficient way of thinking inverse problems. And the aim is to find the so-called posterior density. So probability density of theta, so these unknown parameters, given the measurements y. And from the basic theory of probability, we have so-called Bayes theorem, which says that posterior is the same as likelihood, so-called likelihood, so probability of measurements given the theta times the probability density of prior divided by marginal density of measurements. And this is basically constant here. When you measure your data, it's just a scaling factor and it can be omitted, and only this upper part here is left. Sorry. And this is normally very high dimensional density, probability density, because, for example, in X-ray tomography, normally you have 256 times 256 unknowns, pixels in one layer. And when you think of 3D, you multiply it by 10 or 20. So it's difficult to handle in computational matter these posteriors. So normally what we present as a solution is not the whole density, it is the actual solution, but we take some point estimates. We calculate, for example, mean value of this or the maximum, so kind of largest probability of this theta given the data. So they are reasonable measures what to show as a final solution. And it can be plotted as one image, for example, in X-ray CT. You cannot plot this whole posterior. You have to tell something specific out of it. Okay, then make a couple of assumptions. So if we have Gaussian densities and this kind of additive noise model, so measurements are linear, A times theta plus E. So it's easy, takes a couple of pages to show that the likelihood is actually the same as the density of noise, this E here, that's why we have E here, with the argument of y minus A theta. So it comes directly basically of this functional correlation here. And what we get for the posterior, of course, we plug this in place of likelihood. Now, if we have Gaussian assumptions, we have Gaussian noise. We assume here that it's zero mean with covariance CV, and prior is Gaussian with mean eta theta and covariance C theta. And if we write now these Gaussians and plug them in here, so here we have a product of two probability densities, so it's shown up here. So this is the likelihood, so it's Gaussian with the argument y minus A theta, there's an inverse of noise covariance, times Gaussian of theta, where you have mean of prior is eta theta. And now this maximum a posterior estimate, which is actually the mean of the posterior when we have Gaussian, because it's unimodal and symmetric, so it's the same point. So we can obtain it by minimizing, so you maximize this one, so this one, but it's mathematically the same when you add these, because there's exponent times exponent, so you add these exponents together, and to maximize this is the same as minimizing. Well, you can take a logarithm or take a minus sign out of it, so you minimize the exponent, but having plus instead of minus in front of these terms here. So and now you get the map solution shown down here. So this is already quite a good solution from the inverse problems point of view, because you can solve pretty much of problems when you know what to do. So what you need to know here is the mathematical model. So matrix A, you have to decide what is your prior, what's the covariance C theta, and what is your noise covariance. So let's have a look at these. So matrix A comes from the physics, like in X-ray in this thermometer. So it's normally fairly easy to obtain. So noise covariance is quite often assumed to be uncorrelated, and if it's uncorrelated, so noise covariance is diagonal, where you have variances of all the measurements. So it's M by N matrix where you have only diagonal terms here. Even easier is that this variance is same for all, so then it's constant also on the diagonal. And there are ways to estimate this doing some repeated measurements of your device. And you can choose the prior, for example, in the simplest way, so-called Tikhonov prior way is identity matrix. So it's you assume that the values are just random with certain variance. You don't have any correlation between the different parameters. But very often what we also use is the smoothness of the solution. We assume that the solution is smooth, so we choose this kind of squared exponential covariance function. So each component of the C theta can be computed through this equation shown here. So this is the distance between the all the pixels, pixel I and J, computed there. There's the variance of so how much you assume that the values of theta vary around your assumed mean value. So you put big number if you don't trust your prior, but if you know that, okay, these numbers are trustful that I put to the mean vector, so then you put small number here. And this L is so-called correlation length. If you assume that pixels correlate in large distances, so value of one pixel is almost the same than as the other pixel far away, you put big value for this L. Okay, so then you get smoothness prior. Okay, that was the theory. If you know these, you are always mastering inverse problems to a very wide extent. But let's go to applications. So what we research in our group are biomedical inverse problems, like standard imaging techniques in hospital, CT, MRI, PET, and so on. Then for biomedical problems, we also have some other so-called diffuse imaging techniques, like this electrical resistance or impedance tomography. I'll show some applications of that. Industrial inverse problems, this is mainly my field, so process tomography, so we can apply these certain imaging techniques to industry. I will show examples of this. Geosciences and atmospheric sciences, we also work on like seismic imaging, and then some theoretical approaches as well. We have a couple of small laboratories, this kind of electrical tomographic imaging lab, where we have commercial tomographic devices, and also some of them have been designed and constructed and built by ourselves. So here is actually a picture of that. And then we have this kind of optical and acoustic instrumentation lab. And then we collaborate a lot with, for example, University Hospital just next to our campus, so we get data from the CT and MRI devices quite easily. Okay, so let's have a look a bit of how this electrical imaging techniques work, this ERT and ECT. So instead of applying X-rays, so this kind of a bit harmful ionizing rays, so we put in small amplitude sinusoidal currents through electrodes. So you attach small plates, metallic plates on the surface of object like this cylindrical or circular here, and you apply currents through, let's say, neighboring electrodes, for example. And then you measure voltages of all the others. For example, here you have 16 electrodes. Then you move to this current injection to another point, so for electrodes 2 and 3, and you repeat the measurements. You do this all around your object to collect these projections as you would collect in the CT imaging. And this is for imaging conductivity, electrical conductivity inside the patient. And you need a contact of these electrodes to the object. And ECT is another where you don't need a contact. You can have air gap here, or you can have some non-conductive plastic, for example, between the electrodes and the object. And here you apply voltage and ground the other electrodes and measure the capacitances between all the other electrodes. And then you move this voltage applying to the neighboring electrode and repeat the measurements. And this you use for non-conductive object. And the estimated parameter is permittivity, not conductivity. So ERT works in this way. Here's the mathematical model. When you discretize this, you get this, basically this matrix A, but it's actually nonlinear. So you cannot write it down like A times theta, but this is a nonlinear inverse problem. But here you have the conductivity, you have potential field. This is the current that you inject to the object, and this is the voltage that you measure on the boundary, as explained in the previous slide. And forward problem is when you know conductivity and applied current, you calculate potential on the electrode and potential inside the domain. And the inverse is you also know the injected currents, you measure voltages on the electrodes only on the surface, and you estimate this conductivity distribution inside. So this is just a picture. If you apply currents from here, you get this kind of current flow inside there, and this is one set of measurements on the boundary on these neighboring, on these other electrodes here. And when you do this for many current injections, you get a set of measurements here, and you can estimate conductivity distribution of these objects here. And as I said, this is nonlinear problem. So how you estimate it, it's the same equation as I showed earlier, but now this one here is not A times sigma. This is now the theta here, but it is nonlinear. So you iterate using Gauss-Newton, for example. You start from this example homogeneous value, and through Gauss-Newton you change this conductivity or permittivity, and you get the final result like this. And these are the computed and measured data, so they kind of fit quite closely to each other. Or you can linearize it as well, so that you only estimate the conductivity changes over time, for example, when you have two sets of measurements. Okay, let's have a look. Just one example of the pipe flow imaging. This is from our tomographic lab. One of our spin-off companies, Roxol, came to do some experiments here. So their device is shown here. So there are 16 electrodes attached inside the surface of this pipe. And here now this is just water and air in there. So they have very different conductivity. So you can see here this, let me show when it comes. Yellow up here is air, up here, and the black one here is water. Of course, this is not very interesting for actual real life, but for example, if you have oil and water and gas flow, so then it becomes interesting to be able to see what happens inside the pipeline in the industry. Okay, another application using these electrical measurements of this kind of non-destructive testing of concrete structures. So concrete is very often used material in construction of buildings or bridges or whatever. So 7.5 billion cubic meters of concrete is produced every year. And we don't want this kind to happen, so we would like to follow up and do non-destructive testing, and at least we don't want this one to happen. Okay, this is one application using ERT and ECT, so-called sensing skin. So we have this kind of a concrete brick. This is an experiment that is often done in quality assurance. So what they do, they have a weight here going down, they press down this concrete piece of concrete, and concrete starts to crack on the bottom of the concrete here. So this is the reality what happens up here on the right hand side. And actually you don't see these cracks by naked eye, so it would be good to have automatic measurement device to follow what's happening in the cracking. So what the guys did, this is from Aku Seppänen's group. So they painted this concrete with conductive paint, attached electrodes on the surface, and use this ERT idea. So what happens when when the concrete cracks? It cracks this conductive paint and it prevents the current to flow normally. So in the case where the crack wouldn't exist, so it changes the conductivity distribution, and you can estimate these changes. So down here on the right hand side, you can see the estimated conductivity distribution. So you can see that okay, crack starts to create in the middle, and then also side cracks to the left and right of this concrete piece of concrete. So this can be used in quality assurance tests to automate the measurements or to see how the cracks behave. This is from my colleague in Technical University of Graz in Austria. This is using ECT for flow monitoring in steel factory. In steel factory, they use pulverized coal in producing steel, and it must be transported for long distances, several hundreds of meters, using pneumatic conveying system and nitrogen as a conveying gas. And they want to follow and optimize the flow patterns and flow regimes, how this coal move inside this kind of pipeline. And they used ECT tomographic system to see inside the pipe. And what they did, they developed this kind of a ECT sensor and also electronics for these very, very harsh conditions. Here is the attachment of the sensor in the real site. They cut the pipeline and assemble this sensor in the place. And what they get is this kind of 2D slices over time. So this is time axis here of ECT data. So this is permittivity distribution, and this red one here shows the coil, and the blue one represents the nitrogen. So they have different permittivities, and they can see in the it produces the contrast in the ECT image. So they can see, for example, here that okay, there's coal, so that it's up to the whole pipe in this section, but here only half of the pipe is filled. And when you see inside, you can optimize the flowing conditions of the coal, and it's very important for the production. And then if you can measure the velocity field as well, from this ECT image, you can obtain the density fairly easily through calibration, not very easily, but fairly easily. And when you calculate this kind of integral over this structure or cutting of this pipe, so this gamma, you can estimate the mass flow rate. So you can calculate how much coil goes through the pipeline. So very interesting application. This is from our EU-funded project where ECT is utilized at the microwave drying process of polymer forms. So what happens here is that we have this kind of polymer forms of which they make, for example, window insulation tape. So this kind of tape. And during the production, it needs to be immersed in this kind of impregnation tub. So there's this kind of a liquid that makes the foam fire resistant. And this is very important part of it. So it gets wet, and then they have a big microwave oven. Wet foam goes in, and then it comes out, hopefully dry, so that there's only like 15% of moisture, and so that it homogeneously dry, so that there's no hot spots, so very dry spots or some very moisture spots in there. And what we did in this project is that we developed ECT device to actually measure in tomographic manner the moisture content of this foam that comes out from this big microwave oven. And why you can measure the moisture is that the electric permittivity correlates very well with the moisture. When there's more moisture, like for example more water, the permittivity value increases. So you can estimate the amount of moisture in the foam. And if something is wrong, so that it's not what you want, it's not homogeneous or what, you can make a controller. So you can control these microwave powers transmitters here using this information. So this is fairly complicated industrial application using tomographic measurements to control this drying process. And what we did is that we used commercial ECT from our spin-off company. We built ECT sensor, and this is nice in ECT because you don't need a contact with the object, so you can have an air gap between the sensor and the foam so that it can slide through the device. So this is the output of this microwave oven, so we can measure the moisture content of the of the foam. And these are just a couple of tests. On the left, there's stationary experiment. We just tested whether we see different moisture levels. P3 has some 10% of moisture, P1 some 80% of moisture. So ECT device can recognize different moisture levels quite well. Then we did also dynamic, so that this piece of foam moved through the sensor. It didn't stop for measurements, but it was dynamic experiment. And again, there were different moisture levels, P1, P2, and so on until P13. And you can see that we quite nicely can estimate the moisture levels using this ECT device in dynamic experiment. And then also our students developed a controller, in this case simple PI controller, and here is just a test case to to see how the controller works. So in controller you set some set points or value of the moisture, for example 20%, and in the beginning the power of the device, these microwave transmitters, was too small, so the controller started to increase the power, and finally it reached the correct set point. Then we changed the set point, smaller moisture, so less water or less fluid in the foam. So you need to increase the power again. So it saw this, and the power was automatically increased to bigger value, and finally the set point was reached in the experiment. And there are actually a couple of commercial applications available. So these kind of electrical imaging techniques can be used in in, let's say, real industry. For example, Metso company sells this kind of a tomographic instrument that measures online and automatically so-called air core in this kind of hydrocyclone. And hydrocyclone is used in mining industry to separate fine particles from coarse particles. So all the particles go into this hydrocyclone. They go in this whirling flow, and what happens is that coarse particles drop down here and fine particles go up here. And very important factor in this is the location and size of the air core inside this hydrocyclone. So you have to have device to measure, to see inside the device without, of course, breaking the device. So they have developed this kind of system. And another is Pyroxol, one of our spin-off companies, to detect interface levels of water, emulsion, oil, gas, and foam in this kind of a separation tank. So they have this kind of it's actually a rod that measures outside the rod. So on the surface of the rod, they have electrodes, and they inject currents and measure voltages, and they can detect these interface levels of water. So there's water, there's emulsion, there's oil, and there's gas. And this is important in oil and gas industry in these kind of separation tanks. There are some videos, but I think that we move forward to save some time. And one medical application that is studied in our group by Professor Ville Kolehmainen. So ERT can be used to kind of monitor, to do follow-up in a stroke of a human head. So what happens in a stroke is that if you have hemorrhagic, so there's a rupture in the blood vessel and blood leaks into the brain tissue. So this actually increases the conductivity because blood is more conductive than brain tissue. And there's also a blood clot, so ischemic stroke, where the blood clot stops the flow of blood in certain area. And this actually decreases the conductivity of brain tissue because the blood cannot enter certain areas of brain. So the first idea was to differentiate between these two onsets, these happenings, but it ended up to be a bit too difficult for ERT. So what they ended up to do is a monitoring idea. So what happens, or what it is used, is that when a person comes into the hospital and he or she's diagnosis is done through CT, so that there's hematoma, there's blood bleeding in the brain, or even ischemic happening, and we try to use an ERT device to monitor whether it gets worse or whether it stays stable or whether it's healing. So we do a follow-up from this state when the diagnosis is done in the hospital, and then do the follow-up, like on the right-hand side, whether there's new bleeding or the existing bleeding increases. So why this is important is that CT is done always, and from that we get the so-called computational model for this ERT device or EIT used in here. So this is what we need. We need to know the geometry. And then we attach electrodes on the head of the object, and we start making measurements. So for example, here is kind of a lab experiment done, or actually is it simulation anyhow. So when this blood bleeding, for example, here increases, so you can estimate using this device how this conductivity changes, and you can see that, okay, there's some increase in the conductivity, which means that it has gone worse, this hemorrhagic stroke. And what we have done in our lab is to build this kind of medically safe device. This can be taken to the hospital, and hopefully is done soon this year. There have been some problems to get the permission to do it because it has to go several tests. So medical devices are difficult to get to the actual measurements. For example, they must prevent to apply too high currents to patients and so on and so on. But so far we have used this in the lab, or Ville Koleman's group has used. They have, for example, done these kind of a 3D printed heads or skulls of humans. These are true size of humans, and electrodes are mounted on this skull, and they can make different types of experiments to see whether this device works in phantom studies. And the final electromagnetic device what we have built and studied, this is actually work of Dr. Sial Arif in our group, is electromagnetic flow tomography. So instead of estimating conductivity distribution, we can estimate the velocity distribution, which is very interesting in many industrial applications. So how this is done is that you have this kind of a pipe flow, some conductive flow, fluid is there, you put coils around the object, 4 coils like here, and then you attach electrodes on the surface of the pipeline like this. So these are coils, they create magnetic field inside the coil, and when you have conductive fluid flow inside the domain using physics laws and mathematical modeling, so it creates this kind of a current density inside the domain. So this is conductivity of the fluid flow, this is velocity, and this is the known B field. So it creates a voltage field in the in the pipeline, and you can measure this voltage field using these electrodes on the surface. So what you are interested in when you apply currents here and create a known B field, you measure the voltages on the surface. So you measure this U on the surface of the pipeline, and inverse problem is that you estimate this velocity field V from this data. And this is possible to be done as far as you know the conductivity distribution applied B field. And let's skip the mathematics a bit. And here are some experiments, earlier experiments in the beginning when we got the device to work. So this is a test case where you have a pipeline shown here, and there are two reconstructions of velocity field. On the right hand side, you don't have this blockage inside the flow field. So if the flow field or velocity field is this kind of a parabolic having maximum value of around 2 in here. And when you place this blockage to prevent some of the flow, because same amount of water in this case must go through the pipeline, it must increase the velocity in the center. So here it's 3.2 around in the center. So we can recognize this change in the flow field. And if you have some blockage like this, so water or material must flow on the right hand side, so it must have large velocity on the right hand side here, because all the material must flow in here, and there's no flow on the left hand side, or actually it's negative, so there's this kind of a turbulent flow. This is measured after this block, so some turbulent flow happens after the blockage. And this is just electrical tomography device attached to the same system. And we did some lab experiments. So we had this device of measuring velocity field, and the other device, this ET or ERT device, to measure the conductivity distribution. And why is that done in such a way is that you need to know this conductivity here in order to estimate V. Otherwise, you should estimate both of these, and that's not possible, or it's very difficult from only these data. So that's why we have two devices. This device to measure the conductivity and this device to measure the velocity. And here was our lab experiment that Dr. Chial Arif did in our tomographic lab. So there's EMFT device here, and then there's this electrical resistant device here. So this estimates the velocity field, and this estimates the conductivity field. And these are some results from these experiments. So on the right hand side, using different type of algorithms to estimate these. I don't go into details of these. So you can see that flow is pretty much parabolic. So we had water here and 10% of oil here. And this is conductivity distribution on the left, this kind of vertical slice through the pipeline. So you can see that here we have less conductivity up here, so it's mostly filled with oil, and this red part here is mostly water. They are mixed a bit depending on the value of velocity, and these three columns represent just different types of algorithms how you can do the estimation. We are not going into details of this. And then when you combine actually this conductivity information, or actually a phase fraction, and this velocity field information, you can actually calculate the volumetric flow rate of oil and water. So you can estimate how much oil and water flow through this pipeline. And this information is very important, for example, in oil industry, so that they can get a rough estimate of how much they have, for example, pumped oil from the oil rig. Okay, so there are some conclusions here. So first of all, there are a lot of inverse problems in wide range of contexts in process industry, medicine, geophysics, and so on and so on. Just to mention any field, so you can apply inverse mathematics in those fields. they are often ill-posed. You need to regularize them. And then these soft field tomography techniques using electricity or light or magnetic field. So they are normally fast. You get result quite fast if you do, for example, linearized estimation, but they have low spatial resolution. So the resolution is not comparable, for example, with MRI or CT or something like that. And this Bayesian inversion is a good tool because you can, for example, estimate the uncertainty, the errors in your parameters, what you have estimated, and that's important factor. This kind of uncertainty quantification is big field of research in inverse problems. I didn't show here results of using AI. We have applied this AI approach for this flow field estimation or estimating the volumetric flow rate, and also, for example, in some geophysical applications to estimate the water content underground in aquifers. So this is a growing field nowadays, and a lot of research is done in AI community, and we have also applied these techniques. They are quite efficient. Okay, I want to stop here and thank all of you for listening. Hope you got some ideas of what's happening at the University of Eastern Finland. Thanks.
Thank you. Thank you so much, Professor Marco Faukonen, for the inspiring topics and talks. All right, so we can see here that we have the real connection application between statistics, mathematics, and also physics and industries. And you may have a question. Please feel free to post your question in the Zoom chat or use the raise hand feature to ask directly. So kindly mention your name and affiliation when you speaking. Okay, if you have any question, just feel free to chat or raise your hand. Any questions? Or perhaps on behalf of the participant, may I have a question, Professor Marco?
Mm-hmm.
Okay, actually, what is the advantage of the, you mentioned that there are some kind of approach, deterministic approach and statistical approach or statistics approach. What is actually the advantages of the statistical approach compared to the deterministic?
Yeah, well, there are some advantages as I mentioned briefly, perhaps not very clearly, is that when you do the statistical approach, you can actually solve the whole posterior density, not only 1 point estimate, and this makes it possible to estimate some statistics of the estimate you are computing. So, for example, you can calculate the error values, these uncertainties of the estimated parameters. I didn't show how the posterior covariance that includes the errors in the parameters in the diagonal. So this posterior covariance is easy to obtain from the equations I just showed. And when you know these posterior covariance on the diagonal, you have errors or variances of your estimates, and then you can apply the estimate of, okay, this value is 2 plus minus 0.1, where the 0.1 is the variance or some multiplication of the variance. So you get uncertainty quantification to there. And also then when you have these covariances, they are of the prior, so quite often they are a bit more kind of intuitive, even if they may sound a bit strange, that often you think that, okay, parameter is deterministic and strict, but anyhow you in practice think in statistical way through probability density. So, and when you think of covariances rather than these L matrices, so normally you produce invertible matrices in that way compared to if you think of this deterministic regularization matrix. So you quite often create regularization matrices that are non-invertible, and in some algorithms it causes problems because in some cases you need to do inversion of this matrix. So these are a few that come into my mind.
All right. Okay. Okay. Thank you. Any other questions from the participants?
Yes,
Yes,
I
Prof.
ask a
David.
question. This is just a general comment and question. Also, I'm very impressed with your research of interest because you have been exploring mathematical modeling and numerical methods, not just through computer simulation. I saw in the slide also implementing them directly on the real world devices. That's impressive, I believe. Yeah.
Thank
In
you.
Indonesian scientists, if can achieve that Professor Marco has accomplished, it would be significant to enhance the technological readiness, of course, yeah, in applied mathematics. My question is, in your country, is it easy in for mathematician to collaborate with industrial side? As in Indonesia, such collaboration is still quite challenging. Yeah, so it is not so
Good.
easy to collaborate.
That
For
is a good
example,
question.
yeah,
It is.
we ask to the hospital side and then ask a permission to deploy our coding and simulate with their devices. It is very hard. So could you tell me how is in Finland? Okay, that's the
Yeah,
first one. The
it's
first one. Okay.
yeah, it's
Yes.
not always easy. I mean, we
Yeah.
have contacted several companies over the years and having discussions of possible applications in their field, but no, it's not always easy. Sometimes they don't want to tell if they have any challenges or
Okay.
problems, and they are very quiet of what's happening there. And of course, then it comes to the funding. If we start some project, so we need to find funding for that. And we have like Business Finland in Finland that have this kind of consortia project with companies and universities. So there's funding available, but normally it requires at least 2, probably 4 different companies to kind of be interested in the same subject, research subject. So you need to find these companies who would be, and they need to give some funding there.
Oh.
It's not always much, but it's still
Yeah,
money,
yeah.
real
is
money.
good,
So
but
it's not
so
always easy. With the hospital, you have to find correct persons. Like in hospital, we have really good collaboration because in Finland, in hospitals, they have quite many hospital physicists who have background in physics. They have studied medical physics. So we collaborate with those, and then they know doctors in there. So we quite easily get a kind of project with the hospitals, at least in our university and in our group. Companies are a bit tricky, to be honest.
So actually, who initiate the collaboration? Company invite you and give you
Sometimes it's
as
that they
funding.
contact us, but normally it's vice versa, so that you have to contact
Okay.
companies and
That's
then go to tell about your research and some possibilities. And for example, I have contacted the last year some like 15 different companies over Teams or then visiting. But
yeah, that's fantastic.
yeah, it's you just have to do this
Because
work. I
in
mean, you
Indonesia,
have
as
to discuss with them.
mathematician, normally we got funding primary from a government
Yeah,
grant, not
it's
from
also common for us.
from the
Yes.
industry grant. They don't trust us
Mm.
as
Yeah,
a
it's
Not yet.
practitioner. Is
yeah,
just
it's
use a computer simulation and develop mathematical modeling, discretize, and then convert into non-linear or linear equation system and something like this. So
Yeah.
they don't trust us.
Perhaps in
But
the
hopefully
future.
this is also in our
Yeah,
yeah
it's
our
not
idea.
easy either
So that's why yes
in
yeah.
co-op.
Okay, Prof. Marco, fantastic. But
Thank
for the because also I was working on the numerical analysis when I was in UK. Normally, if we have modeled what a phenomenon from the real world, and then we end up with the mathematical modeling. And finally, we should discretize, yeah,
you.
the mathematical model.
Yeah.
And you say that uh, in your case, often the result end up with the nonlinear equation. Yeah, so
Yeah,
for
quite often these are
nonlinear,
non-linear.
yeah,
Mm.
equation. So do you have recent numerical method, the most effective numerical method to solve the nonlinear equation apart from
Well,
yeah
what
okay
comes to nonlinear inverse problems, so we quite
okay
often use Newton's type techniques.
Newton okay yeah.
Yeah, like Gauss-Newton, where you approximate the Hessian with
Mhm.
certain approximations. So, but there are some others. We have used some others, but not. I haven't used very widely.
Yeah,
Very
yeah.
widely. But some of them are also linear, like these, especially these hard field techniques in hospitals, CT and MRI and SPECT and PET. So they are linear. So, but the soft field using electricity or light or magnetic field. So this flow tomography is actually linear, but electrical imaging is nonlinear. So Gauss-Newton is because it quite often converges quite nicely, but it
Yeah.
requires a bit of computation. Yes, it's not that
So
easy.
sometime in the what ablasan study of fundamental sides of this, the indicators when we publish a paper for the finding or studying the effectiveness of the specific numerical method, normally they often evaluate and criticize about the first or the very important indicators like number of iteration, number of
Mm,
floating point operation,
mm,
then time
yeah,
elapsing, and also the convergent error, the history of
mm.
convergence and complexity analysis. So when you are dealing with the real devices, do you include this kind of indicator in your study when you are writing a paper, or you compare between the real data from the real devices and your simulation?
Yeah, what is normally reported is of as you said, the iteration, number of iterations and the time of calculation, because that has specific meaning in real world applications, because if the computing a solution takes too much time, so you might be late. I mean, if you need to solve iteratively certain systems, so then it takes of course time. And yes, we need to do it. But quite often, what we do in these nonlinear cases is that we use we linearize the problem, and then as there was in the one slide, so we need like two measurements, so we don't estimate the absolute value, but we estimate difference between two time steps. And that is useful when you monitor something, and when the value that you are estimating changes over time. So sometimes it's enough to only show the difference in the estimation, and that can be done online basically. That is fast, and then you can overcome this problem with the iteration time. But yeah, you definitely have to consider the iteration time. And
Yeah.
sometimes it's kind of Sometimes you can do calculations offline as well, so that you give quickly some result that is a bit coarse, and then you do the computation offline to get more accurate results that can then brought in a later time step. So that's also an option
Yeah,
to
that's
improve the result offline,
yeah, interesting, very interesting.
depending about the case that you are
Yeah, when I
applying your.
was in Malaysia, solving what numerical problem, linear or nonlinear equation,
Mm.
they now start using quantum computers.
Mm.
Yeah, and they combine with the machine learning. So,
Mm.
and also I have a postdoctoral research fellow. We combine quantum computing and machine learning. So
Yeah,
I'm
yeah.
not sure, but they say that it is very faster. Normally, we use conventional computers, takes like a certain period, then it will be
Yeah, that's a
cut
good
until
point. Yeah.
50% or something.
And of course, as you mentioned, this AI, artificial intelligence approaches, what we have
Yeah.
already applied to some cases, they
Okay.
solve the nonlinear problem directly
Yeah.
if,
Okay.
when you have the training data available. So
Mm.
whatever nonlinear problem you have in hand, so
Yes.
because the neural network is a nonlinear mapping, a general nonlinear mapping, so you can solve very quickly
Yes.
nonlinear problems. Yeah,
Yeah, but
that's one option.
the weakness is sometimes we are not satisfied because there are a lot of black box
It
in
is,
the
yeah, that's the
artificial
problem. And to get the training data, that's another problem. I mean,
training data and testing. We do
you
not
need
know
to
the
simulate a
process
lot, or you
behind
need
them.
to have access to some measurements. So that's sometimes tricky.
Yeah. Okay. Thank you
Yeah.
very much. Very
Thank you.
fantastic. Very
Thanks a lot.
fantastic. Yeah. It's very good. Yeah. Okay. I give it back to moderator.
Thank you.
Yeah.
Thank you so much, Professor David, for the discussion. It's quite interesting discussion. Okay, last thing, maybe you have one more question, or if not, we can conclude and close this session. Okay. Okay, let us conclude our speaker session for today. On behalf of Indonesian Mathematical Society, I would like to sincerely thank Professor Marco Falconen and Professor Basuki Widodo for sharing such valuable knowledge with us. Thank you also for your coming, to all participants for your presence here today, and we hope to see you again in the future events. Wassalamualaikum warahmatullahi wabarakatuh. Thank you and have a great day. I now return to the session to the Master of Ceremony. Anis, please.
Yes, sir. Thank you very much to Ziaul Arif MSc PhD for moderating the session. Ladies and gentlemen, time goes so fast, and now we are entering the last agenda. That is closing and documentation. To all participants, please turn on the camera. Thank you. We will take the documentation on count on 3. 1, 2, 3. Once again. 1, 2, 3. Thank you very much.
Thank you.
Finally, this is the end of the International Seminar Advances in Computational and Applied Mathematics. Let me close this event by saying Hamdalah. Alhamdulillah.
Alhamdulillah.
For
Thank
the
you,
last,
Anis.
I do apologize if there were mistakes. Thank you very much for your kind attention. Wassalamualaikum warahmatullahi
Waalaikumsalam.
wabarakatuh.
Waalaikumsalam
Terima
warahmatullahi wabarakatuh.
kasih semuanya.
Terima kasih,
Mohon
Prof.
maaf
David.
ada kesalahan, Pak Zdi,
Terima kasih, Prof. David.
Bu Sumiati. Terima kasih Ibu Elvi, Pak Adi Surya, Pak Tri Mariono. Ini yang saya anukan yang dari luar, Pak Irwansyah. Mudah-mudahan semangat selalu. Oke.
Terima kasih, Prof.
Oke,
Thank
Mohon
you.
izin,
Bye-bye.
Monggo.
mohon izin, Lip.
Alhamdulillah. Mudah-mudahan berguna. Pak Zi mungkin slide-slide-nya Pak Zi barangkali berkenan di-share teman-teman.
Iya,
Ya.
Prof. Nanti
Iya.
saya coba share
Hmm.
ke produk.